Hello, everyone. Welcome back to the question and answers. And it actually works now. You guys might not be aware of this, but at the European African Q&A session earlier, we had a Crowdcast outage. So we broke that part of the internet too, apparently. I'm not quite sure whether it was really our fault, but it seems to accumulate and the coincidences seem to become less and less credible. So anyways, I'm very happy that you could all join us. I hope you had a great day. So today was about model fitting, and this is the third day, and I know that a lot of you are starting to experience sort of like this feeling of being overwhelmed. Lots of materials getting thrown at you. It's becoming complicated. There's equations. Late hours working on projects and Q&A and brainstorming. But really what I want to tell you is that this is absolutely normal for a summer school. You are supposed to be overwhelmed. You're supposed to be bombarded. You realize we're throwing at you essentially a whole PhD worth of material in 3 weeks, right? And so in no means should you expect to digest that all in all the details. But hopefully you'll come out with more knowledge than you had when you came in. And in particular, a better overview of what the field is like and where to start if you want to take a deep dive into one of the, or multiple of the aspects that we will be teaching or have taught already. So I really just want to reassure you that this feeling of being like lost, this feeling of being overwhelmed, this feeling of there's so much uncertainty, I don't even know where to start. This is all perfectly normal. It will get better towards the end. But part of the suffering, part of this sort of like, hanging out together as a group and suffering through this together, this is what makes a summer school experience. This is what creates the bonds, the lifelong bonds that come out of summer schools. And this is what creates memories that you will keep and cherish forever. Okay, so with that, I don't want to say any more about this. It's my great pleasure to introduce our 3 guests. So we have Anqi Wu, we have Jan Drugowitsch, and we have Patrick Mineault. Anqi Wu is actually the author of the tutorials you had today, and she is a postdoctoral fellow at the Center for Theoretical Neuroscience at the Zuckerman Mind, Brain, and Behavior Institute at Columbia University. Jan Drugowitsch is a professor in the Department of Neurobiology at Harvard Medical School. And Patrick Mineault is our very own special guest. He is our tech guru. He essentially makes everything happen. And no, it was not his fault that Crowdcast broke.
It was all your fault for all being there at the same time.
So I'm going to go to reverse order now. Patrick, do you want to tell us something about what models do for you in your life and why you think model fitting is important and what you can get out of model fitting?
Yeah, absolutely. So we used to joke in NMA that there's a little, because NMA is really the underlying principle is meta modeling, right? Like, how do you do modeling and how do you apply different approaches to different kinds of situations? And we used to joke that there was a meta modeling that was happening inside the Slack, because essentially, like, all these processes that we're teaching you right now, we're also using them to actually run the school. So one example is when we first ran the students, when we first ran the student survey, we didn't know what kind of people to expect that would come to our school. So we had 18 different questions that we asked, like, how do you feel about LFPs? How do you feel about spikes? How do you feel about lift models, about this and that? And then we had just so much data from so many people, and we wanted to extract that down to a small amount of factors. And what we found out is actually there's 3 underlying factors. You know, some people are more biological and computational, other people at earlier stages in the career, and then later. And some people are more micro and other people are more macro. And that's an example that really like helped us to understand who was our audience. And so we've run a lot of this this kind of analysis, and I can't wait for you to see actually what kind of analysis that we ran when we crank out some papers right after the school. But first, we're going to need to sleep for several weeks.
Thank you, Patrick. Jan, do you want to say a few words about yourself and about, the role of models in your life?
Sure, happy to. So my background's actually in probabilistic machine learning, and then I moved to neuroscience as a postdoc, so I've got very much a machine learning perspective on the whole thing. I run a lab in computational neuroscience where we do theory only. So we do work very close to data, which means we build a lot of models and we try to figure out how these models fit the data. So the models we built are, on one hand, about neural activity, trying to figure out how uncertain information is encoded in neural activity. And on the other hand, there are decision-making models where we're trying to explain behavior and also neural activity. So one thing that's very important for us is fitting these models to data, which is basically the content of today's tutorials, and also comparing lots of different models. So it's really our bread and butter to use all the methods you've heard about today in our everyday research. It's really central to the approach that we take.
Awesome, thank you. And finally, Anqi, so you saw that there's lots of comments already in the chat thanking you for the amazing tutorials and the great explanations. You should read those because they're really they're super nice, and I'm really happy to read them myself. but maybe you can give us a little bit of an introduction to yourself, and then also what do models and what does model fitting do for you?
Yeah, sure. Yeah, similar to Jan, actually, my background is very machine learning. I had a computer science master degree. So in earlier years, I've been working on pure machine learning model or probabilistic machine learning model to different applications. Then I got the chance, starting my PhD, I got the chance to work with neural data. And I think it's a brand new world. It's so interesting to not only develop an interesting model, but apply to the brain data to analyze the brain. So that's how I start to work on this kind of problem. And thus, model fitting is actually the main workforce or the main thing in machine learning. All people do is to come up a model and fit to the data and try to explain the data and maybe do classification or prediction. So anything, from my perspective, anything about data analysis or data fitting is all model fitting. And then, yeah, and I think it's really powerful because in many problems in neuroscience, people, how to say, people used to rely on very biological model to understand the data or do more theoretical kind of work. But I'm more like statistic probabilistic machine learning person. So all my tasks are coming up with interesting machine learning model and use that to fit to the data. And usually you can find really interesting thing that can explain the problem or even come up with some hypothesis for experimentalists to do their research. So I think model fitting is definitely not all in neuroscience, but it's very helpful tool for both theoretical and experimental neuroscientists to do their research as well. And I'm very happy to be like a more modeling person, try to help people to do their research, and myself also really interesting in neuroscience. So I'm happy to be like this kind of person to, yeah, do this type of research. But yeah, model fitting is very important. It's like a bread and butter for me.
Awesome. Thank you so much, Al, for sharing those experiences. So I suggest we go and answer a few questions now. So the first question is by Maximilian Nentwich. And he asked, are there any recommendations how many folds to choose for cross-validation and how to split the data, segments, or in brackets, segments or random samples? How do these choices affect model validation? Who would like to give that a shot?
I can say something. Oh, Patrick. Okay, I'll have some quick sentence. Sorry, my experience is usually people don't do many folds, like 3, 5, 10 would be the most, no matter how large your data set is. Like my experience is like 5, 10 might be reasonable numbers, but like usually the more the better from statistics point of view, but definitely the more folds you have, the more computational burden you will suffer from, because you need to do the same calculation for the number of folds iterations. So like in my tutorial, I talk about leave one out, and there is actually some good theoretical property of leave one out, which means you only use one data point as the test point, and that's actually an extreme case where you have the same number of folds as the same number of data points, and there is some really good property of that, but empirically it's really computational heavy. So so my suggestion, if you really want to do cross-validation in your experiments, maybe you use 5-ish or 10 at the most would be a reasonable number. But the more folds, I think the better the model should be, more generalizable and robust to even abnormal data points or something like that. Yeah, that's my experience.
Patrick.
Yeah, well, to your point, and just to add to that a little bit, generally, if you have smaller data sets, it's better because the variance is going to be lower if your folds are more numerous, then it can be worth it. So, you wouldn't leave one out cross-validation if you had 1 million data points and you fit a big, deep neural net. But if you had 100 patients and like that was your only data set and there was no way, like each data point is worth 5,000 buckaroos, then you might want to roll out leave one out cross validation. But agreement, 5 or 10-fold cross validation is probably the way to go for most kinds of experiments in neuroscience.
Yeah, and anything you want to ask?
Yeah, I think there was just one part of the question that was not directly addressed, which was the question of how you choose your subsamples. Basically, if you just actually split them by folds or if you just randomly subsample. And so I think the aim here is that we want to fit on data sets that are sufficiently different from each other, because you want to make sure that you're not focusing on a particular data set that you're overfitting. Right? So in that sense, random subsampling is probably not as good as doing the fold-like structure that was introduced in the tutorial, where you make sure that you really fit on different data all the time, like sufficiently different data all the time.
Awesome. So part of the question, I'm not quite sure whether that really got answered, was how do these choices affect model validation? So validation is sort of like a very strong word in terms of modeling, I think. Any thoughts on that?
So I'm not sure what's meant by model validation. Is it in the sense of like selection, like selecting which of a couple of models you should choose from? Or
yeah, I would more see it in the sense of generalization, maybe. Like how valid is this model in a more general sense?
So your estimates are always going to be, your estimates of your cross-validated R-squared or your cross-validated correlation coefficient always going to have larger error bars if you have less folds, right? So it really depends on the power that you have originally in your data set. If you already have plenty of power because you have plenty of data, then it becomes much less important, the actual number. But people never, ever tune the number of folds that they have. It's not like they're running with 4 folds. They're like, this doesn't work. I'm going to use like 10-fold. It's just, generally, it's just a thing that they decide beforehand. But usually the intuition, I think what Anqi said is like the standard thing, which is, you just pick 5 or 8 or whatever, and you roll with it.
Cool. Okay, the next question is by Igor Zverev. Igor asked, why do we describe noise as a normal distribution? What's the mathematical intuition behind that? And then there's some instruction on how we should answer this question. Please do not answer something like, usually noise is distributed like this. Give an explanation to why it is so. Thank you.
I can explain that because so in this model fitting tutorial, we start to learn model fitting. We start to we start to learn MLE estimator. So I didn't really extend or talk too much about other type of noise. But first, here I'm only introducing Gaussian distributed noise. One reason is because first, Gaussian distributed or normal distribution is like the most powerful or popular kind of distribution that can describe many distributions in nature. Like many like occurrence or events can be described by Gaussian more than other distributions, if you have knowledge about other distributions like Poisson, Bernoulli, and all the others. So I think from a probability point of view, it's more possible that you use a Gaussian distribution to model the noise and you will get better fitting than using others. That's one thing. But of course, there's some requirement about the noise. If you observe that your noise can be very negative to positive and there are continuous values across this entire real domain, then usually people pick Gaussian. That's like the first choice. And if you don't really see good model fitting, then you might think maybe the noise has some other distributions other than Gaussian. And then that's the time you will choose other distributions. And if your observation are discrete values, non-negative, which we're going to cover that in day 3 tomorrow, then you might think about also other type of distribution like Poisson or Bernoulli that are usually used to describe those kind of observations. So I have to say Gaussian is just a quick sum is Gaussian the most common distribution to model the natural like events or distributions, and it's very powerful, and it's likely to have a good model fit starting with a Gaussian. And if you don't see good model fitting, then you can explore other distributions. I don't know if that makes sense to some people, or that yeah, you can add more things to that.
Anyone want to add something? Yeah, Jan?
Yeah, I just have a few additions. I think that's it's a good point that Gaussian very often works really well. One of the reasons that's often cited for this is if you mash together lots of different sources of noise, you can imagine, for example, you've got a neuron that's highly connected to other neurons that provide noisy input, then by the central limit theorem, the collected noise becomes close to Gaussian. It approaches Gaussianity. And that makes Gaussianity, like a Gaussian assumption, a very natural one to make. Another thing I'd like to mention, which I mentioned in my intro video, is that you should still be aware that you can't explain outliers well with Gaussian. So if you assume Gaussian noise, you will be prone to outliers. Your fits will be prone to outliers. That is a caveat. The last thing is that, and maybe you'll get into this later in the course, I'm not sure, that the Gaussian distribution has super nice mathematical properties. It is the nicest distribution you can imagine from a mathematical point of view. And so very often it is used, even though we know it's slightly wrong, just because the math works out so much nicer than if you use other distributions. And that's, I think, personally, very often I just start with the Gaussian distribution because I know I can do the math. And then I check if it makes sense. If it's just a bit wrong, I just say, yeah, that's good. Just because the math is so much easier with the Gaussian distribution.
Yeah, that kind of brings us back to what you've learned the last 2 days, like not today, but the 2 previous days, is that when we think about models and model diversity, one of the aspects that a lot of people care about, especially if they come from a more mathy background, is the elegance or the beauty of the model, right? And the Gaussian distribution is part of that. It makes things much more elegant than if you have like another distribution. Patrick, do you want to add something?
No, I think I'm going to take the next question. That was nice.
Awesome. Thank you so much.
Just one quick thing I want to add to second Yan is in the tutorial, right? We show MSE is equal to MLE, but it's only true when it's Gaussian. And when you have different distribution, the MLE solution would be a bit different. Sometimes, in most cases, you don't have a closed form solution. So that's like one like sign of using Gaussian and how much convenience you will have by using Gaussian distribution. Yeah,
that's a very good point. Okay, so the next question is by Angel. How to choose how much % of data to use for bootstrapping? In the tutorial, we did 15 out of 30. Does this choice affect the confidence interval we get for a parameter? That's a great question. Who wants to give that a shot?
So how many bootstrapping samples total that you use?
Well, so I don't actually know about the details of the tutorial, but Angel says the tutorial, they used 15 out of the 30.
Yeah, use more bootstrap samples. It depends on what the on what parameter that you want to use, of course. And I'm really sorry to say that the answer is almost always like it depends. If you want to get the bootstrap distribution for a mean of a distribution, for instance, you can get away with using as little as I think like 6 samples really for your bootstrap. But as you get to more and more extreme distributions, your power decreases to actually infer these parameters. So if you wanted to, for instance, estimate the variance of a variance, so for instance, you have a distribution of people's heights, and you want to see, like, if you had picked a different sample of people's heights, what would be the variance for that sample and how that variance changes across samples, you would need a lot more than 30 or 15 bootstrap distributions. You would need at least 100 or a couple hundred. And then if you wanted to look at extreme distributions, like if you wanted to find the bootstrap distribution for like the 95th percentile, you would have to crank it up to 500 to get reasonable error bars for the bootstrap distribution themselves. So it depends on your power to estimate, but generally for central tendency, you have to have less. For variance, you have to have more. And for like extreme quantiles, you have to have still more.
So
yeah, go ahead.
Oh, okay. So I think the question about 15 instead of 30 is in the tutorial, like before the bootstrapping, we use 30 data points, and then you can get some good fit. And then when you get to bootstrapping, the tutorial reduced the number of data points from 30 to 15. And I think the reason the tutorial is set up that way is because now you have less data points and you are highly possible to have larger uncertainty. And that's why, or that's when you use bootstrapping, you will see a widespread like histogram of the of the parameter distribution. And then you might have a better sense about why bootstrapping is usually helpful. My understanding is bootstrapping is extremely helpful when you have large model uncertainty. And that's probably why the exercise generate 15 type data points instead of 30 data points.
It might be good to just clarify the difference between the data sample and the bootstrap sample.
Oh, okay. Yeah, data sample is just like how many data points you have. Like from at the beginning, what you only have is the data, and then you have data points. Basically, if you plot them right from the x-axis and y-axis, you will see the dots on the figure, and that's the data points. And bootstrapping do samples, replacement samples from those 15 data points. I don't know if that makes sense, or I have some explanation in the tutorial as well. Like maybe I shouldn't say data sample. I should say data points, and those are the given, the observations. And then when you do resampling, you're doing resampling from those 15 data points. Maybe that helped to clarify things a little bit.
Yeah, there seemed to have been some confusion there about what exactly happened in the exercise. Okay, the next question is by Augustus Dorico. If k-fold cross-validation and a KK information criterion are both methods of model selection, what are the trade-offs of using each? Or the pros and cons, I guess.
I can start.
Yeah.
So if you use cross-validation, you need to split your data set. So that means the model fitting can't be done on the full data set. That's certainly a disadvantage of cross-validation because you're reducing your power. You need more data. On the other hand, cross-validation does not make strong assumptions about how the model looks like. It is extremely flexible about the nature of the model because it doesn't assume a priori a particular structure underlying the data. It's very data-driven. On the other hand, if you think about AIC, AIC makes strong assumptions about the data and how it came to be. In particular, it assumes something that is close to linearity. Once you move away from a linear model, if you become highly nonlinear, then the complexity penalization by the number of parameters is not exactly the adequate anymore. So you might over-penalize your model, for example. Because then what matters is what's called the effective number of parameters, which might not be the same as the actual number of parameters. And that's measured slightly differently. So you make more assumptions about your data, but you can use all the data for model fitting. So this is a very coarse distinction between those two model comparison methods.
Cool, thank you. Anyone wants to add something to that?
One thing I want to add is, on the other hand, like why AIC is still valuable. One reason I can think of is cross-validation. First, like Jan said, you have to do split, but AIC you don't, and also how to say, cross-validation you can't really differentiate the hyperparameter, right? So you do cross-validation. And AIC, in many cases, you don't have to do many splits, and you can write down one objective function, and you can optimize that part, and you can just do one run, and you might get a more generalizable results. So that is, I think, one thing. Maybe AIC is still useful, not like still useful and valuable to be introduced to here. Like my experience is cross-validation because of the multiple splits. You have to have you have a lot of computational cost, but AIC you don't need to do that. You just do one run and you get better generalizable model. So that's my experience of using both.
So we got a related question by Pavitra Resheswaran. We did not talk about R-squared today in the module. I was wondering what would be the advantage or disadvantages of using R-squared over cross-validation?
Well, the raw R-squared is just the amount of fit, right? So it doesn't take into account the number of parameters. And I think one thing that we talked about in today's tutorial, or was referred to, is this idea of Occam's razor, which is essentially, if you have two models which are equally good at explaining the data, then the one that's the simpler is the good one. And then there's another similar thing which says if you have two models which have exactly the same complexity, and and one of the models is a lot better at explaining the data, then that model is probably better. And then there's the question of like, how do you trade off these different things? Like how many US dollars do you get for your Australian buckaroos or whatever? And which is what something like AIC criterion is about. So a raw R-squared value doesn't have any consideration about the number of parameters that you have. However, you can use the R-squared that you measure on the cross-validated folds in order to get an unbiased measure of prediction performance. And so the R-squared is good, but it needs to be the cross-validated R-squared. And not the fit R-squared, which is over-optimistic.
Okay. Next is a question by Alex Ivanov. In the tutorials, we are taught the classic bias variance trade-off. However, for a very large model, like neural networks with many layers, adding more parameters can improve test error. Can you comment on this double descent phenomenon? Who wants to give that a go?
I can again give it a try.
Yep.
So just to bring everyone on board what that means, in the tutorials, or also in the introduction lecture, we had this graph where we had model error on one axis and model complexity on the other axis. And you saw that the bias decreases with increasing model complexity, the variance increases, and the actual model error is a combination of both. So it first goes down and then it goes up again with model complexity. Now, it turns out this is not the full story. This is the classical statistical story. But what's actually going on in some learners, for example, modern neural networks, deep neural networks, or some versions of these deep networks, is that the error actually goes down, then goes up with model complexity, so basically complexity of the network, and then it actually goes down again, which is something that is actually very baffling. At least it was to me when I first saw it. That's known as double descent. And it is still a very active area of research why this is actually happening. The current interpretation of this is that in that particular mode, these learning methods operate more like kernel methods, which are a form of interpolation between data points that they've seen, and that avoids overfitting. And that interpolation actually works better if they have more parameters. It's not true necessarily for the very simple models that we talked about today, but it can happen for more complex models. But that's a whole different regime of model error.
Anyone wants to add something? Who wants
Yeah.
to? Yeah.
I think when deep learning start to get really popular and overwhelming in the field, people at the beginning people feel like it's really mysterious or something. Like people don't really know the reason because it's kind of against previous knowledge about the more parameters you have, the more complex the model is, and the less generalization performance will be. But yeah, deep learning seems to be against that. And so, as Ian said, it's a very active field. People throw a lot of energy and time to study from both empirical side and as well as theoretical side. So I've seen paper or I've seen talk try to analyze the structure, like the landscape of a network, and try to explain why different depth of network and different width of the network could, why they could, what kind of landscape it would be and what kind of generalization they should have. But like here, I can't really explain why this is happening by just a few sentences. Like, I just consider that to be a really magic world that me or some people don't really have a lot of understanding about. But when we get back to the simple model, I think the bias-variance trade-off is always true, which people already have a lot of knowledge and study about. So, yeah.
Awesome. So the next question is by Alex Sheffield. In a tutorial, we found that MSE and MLE gave equivalent solutions if our noise is assumed to be Gaussian. Why then would we choose one over the other? It seems like MLE is more versatile in that we could choose a different noise distribution. So is it ever preferable to use MSE?
I can quickly say that because from my perspective, I think MSE is easier. So as a lecture or as a tutorial, it would be nice to introduce MSE first because it's more intuitive. Like you just compare the difference and you minimize the difference. And then from MSE, we can introduce MLE with Gaussian, which people can see a lot of a connection. Although the model get more complicated with noise, but still it's easy to understand MLE if you introduce MSE first. So from my own experience, actually, I don't really use MSE as an optimization like objective. MLE is usually my first choice. Here I'm introducing MSE is more for like the laying the ground or the knowledge base ground for MLE. But however, MSE is usually used as a evaluation criterion. Like people talk about R-squared, you can also use MSE to evaluate how different the model prediction and the true observation are. So yeah, like
why do you prefer MLE?
Because as you said, or as people say, MLE is more flexible. You can consider Gaussian noise or all different kind of noise. So, and it's actually in the future when people talk about Bayesian model, they all built up. They build Bayesian model upon MLE, or it's very similar, or it's very easy to connect MLE to more complex Bayesian model. So my suggestion is you can directly use MLE if you're already very comfortable about this kind of model. You don't need to start everything with MSE, but you can use MSE as a criterion to evaluate the model. Yeah.
Right. Thank you. Anyone wants to add something to that?
Yeah, I think I'm gonna stand up and defend the MSE because I like it. So there's two reasons I'm gonna do that. So I used to work at Google where I was doing analysis of like very, very, very large data sets, like billions of rows. And one thing that happens when you have this kind of data set is like anything that's like fully Bayesian, you just have to forget about it. Like what you get are summary statistics, essentially. So, you know, the mean is an example of, I mean, it minimizes the mean squared error as a point estimate of a measure of centrality. Sorry, I'm not explaining this well. But what's nice about the MSE is that you can run it in an extremely parallelized way. You can calculate a mean in an extremely parallelized way because it's simply reduction. If you wanted to do that with like some parameters of a Poisson distribution, I mean, at scale and parallelizable, it becomes a real research problem. It becomes very difficult. And even in neuroscience, that happens that sometimes people use Gaussian noise model, even though they're really, really not supposed to. So one of my favorite examples is, for instance, if you do calcium deconvolution. Well, we know that, you know, spikes, you can have 0 spikes, you can have 1 spike, you can have 2 spikes. There's no such thing as a negative spike. There's no such thing as 0.1 spike. But if you look at, you know, the famous papers from the Paninsky's lab, for instance, you know, they very, very almost always, you know, assume that the noise is Gaussian, and then you get an estimate which is related to the MSE, except that they tend to add like more constraints so that it's not as silly as I'm making it seem. So there's a lot of, and the other thing is that you can turn a lot of problems into least squares problem. So we're going to talk about GLMs tomorrow. If you do like a binomial GLM, or if you do a Poisson GLM, you can turn it into something that looks very much computationally like a least squares problem. It's called iteratively reweighted least squares. And it turns out that, you know, you can solve a GLM as basically like a reweighted least squares problem. So there's very, very, very good reasons still to learn MSE.
Yeah, thanks, Patrick, for standing up against me. So because I've been thinking from a very Bayesian perspective, so I'm more like a MLE, anything I would think about noise. But I agree that kind of reminds me, like in many real like practical problems, people really start from minimizing a prediction, the difference between the prediction and the data observation. It's like neural network, right? Neural network, the starting point is MSE, and then people do back propagation from. I mean, if you do regression model, you compare the continuous output with the continuous observation, and you do MSE, and you do back propagation. So that's like the first neural network model I learned. So I shouldn't say like MSE is useless. You shouldn't. Yeah, that's probably a wrong claim. Thanks for supplement that point.
No, I just wanted to add a little bit of tension. You know, it's I think it's good for the audience.
Yeah, that's right.
Jan, any more controversial opinions?
Yeah, I think MSE is completely useless. No, I'm kidding. So I think all of those points were really good. I want to make a slightly more general statement about error minimization versus maximum likelihood, because those are basically MSEs on the error minimization side. Using maximum likelihood with Gaussian noise is effectively the same formally, but it's a different look at the problem itself. So what I like about the maximum likelihood approach is that you need to write down a likelihood, and that is basically making very explicit what you assume about the model. So it really says, this is how I think the noise looks like. And that can sometimes be overlooked in the error minimization, from the error minimization perspective. On the other hand, sometimes you just don't want to specify such a generative model. You just want to say, I want to minimize this specific error. That's an equally valid approach. It doesn't come with the benefit of making these assumptions explicit. But if you think of PCA, which is an unsupervised method, so it doesn't fully fit into what we heard about today, PCA was originally developed as maximizing variance in particular directions. Right? You want to find directions that maximize the variance of your data. And I think this is a very useful perspective. After that, a probabilistic perspective of PCA was developed, but I'm not sure how much it adds to the original perspective. So it is not always much better to use the probabilistic perspective. Sometimes the error minimization perspective is just fine.
Great. Thank you so much. Okay, are the other two panelists happy with that answer, or do you want to push back?
I agree. My answer is always it depends.
Right. Okay. Let's take the next question by Zach Friedenberger. Are there limitations to bootstrapping? When should it not be used? Or should it always be used?
So there's this funny thing. So I was going to say, like, well, if you have a giant data set, then you probably shouldn't use it. But I'm actually wrong, because there is this. So one issue with the Bootstrap is that you have to choose with replacement a set which is as large as the original set, right? So if you have 1 million data points, you have to choose 1 million new indices, and that's very hard to parallelize. But there is actually a trick that's very poorly known, which is called the Poisson Bootstrap. And so if you want to Google that, it's kind of a fun technique. But that means that you can generalize the Bootstrap actually even to cases where you have billions and billions of rows. But I think people don't necessarily use Bootstrap that much. It's pretty like if you have a deep net, you don't use Bootstrap.
Yeah, so I totally agree. Actually, I couldn't think of why people. I couldn't think of a downside of bootstrapping from modeling perspective, because it's ignorant about the model, right? You can have a black box. You can just. I mean, like, it's just sampling the data. It's not very model dependent or something. The only downside thing I can think of is the computational wise, like when you have to sample for 1 million times. But if, as Patrick said, there are some tricks to do that, then I don't really see why people don't use bootstrapping. But same wise, I don't really use bootstrapping very often. Agree. Like, it doesn't seem to be a very popular tool people use, although it's always emphasized in a basic modeling course. But people don't really use that very often empirically. On the other hand, I think people in statistics, you really use bootstrapping a lot for hypothesis testing or something. At the beginning, I tried to explain bootstrapping from using some statistic language, and then we realized that it's probably too much. Then we don't do that. But I think bootstrapping is very useful when you do hypothesis tests. I mean, many neuroscientists also do hypothesis tests, like try to analyze on their data to see what's the p-value, or for people who probably have heard of this, and bootstrapping might be more useful like that. But in general model fitting, maybe it's not that popular, or I shouldn't say it's not useful, but I'm just saying I actually don't know why people don't really use bootstrapping that often. But yeah, maybe people have different opinions.
Yeah, anyone add something to that?
Just a small comment. I think bootstrapping becomes problematic if you've got a small data set, particularly because bootstrapping is applied by resampling your data. And in the most extreme case, imagine you only have 2 samples, then there are 3 possible ways of resampling that data. You choose the first data point twice, the second data point twice, or the 2 of them, right? And that clearly doesn't give you very good statistics. But this is a bit of a cop-out answer, because if you only have very few data points, you have a bigger problem anyway. Bootstrapping is one of the things you shouldn't do with that, but there are many other things you probably shouldn't do with that.
Indeed. But the nice thing about bootstrapping, this is why I like it personally a lot, is it doesn't make many assumptions. And you can compute all kinds of things without caring about the statistics or the exact distributions or any of that. So I really like that. Okay. The next question is about, I think we have some time, for maybe 1 or 2 more. From Therese Koch. Under what conditions could the noise in our data not be normally distributed? And how would we know?
This question might be better answered if you finish tomorrow's tutorial, because that's going to be the case. In tomorrow, day 4, we're going to focusing on 2 observations whose noise are not Gaussian. One is Poisson, one is Bernoulli. But yeah, the short answer, if you have data like Poisson spikes or spike trains, where you have all non-negative values and then you have discrete values, then it doesn't make too much sense if you fit Gaussian. And you will actually do an exercise to fit a Gaussian model to Poisson spiking data, and you see bad performance. That's when you will switch to a better distribution. I think it's fair to postpone answering that question tomorrow. So Therese, if you're here, please keep the question in mind tomorrow. If you still have the same question, please do ask it again. So let me get another question here. How does non-independency of samples, how does that affect the likelihood calculation? And if there is interdependency essentially of samples, can you somehow circumvent that issue? Or is likelihood not computable in this case? Independency in the data sample means each data point might be dependent on each other. Is that the question? Yeah,
I think it's going in the direction of time series, for example, or some other dependency, for example. Yeah.
Okay. Yeah.
Okay. So in the intro, I introduced it because it's very convenient that if you've got independent samples, you can just sum the log likelihoods to get the overall log likelihood of your data. If you have dependencies and you know you have dependencies, then you just can't do that anymore specifically. So you'd need to change your model that explicitly models these dependencies, but you can still use a likelihood approach. It's just that now the likelihood function, the log likelihood function, for example, is not the sum of the log likelihoods of the individual trials anymore. For example, if you've got a sequential model where you assume that your current sample depends on the one in the previous trial, let's say, then you will build a likelihood that says, what's the probability of the current sample given the previous sample, right? Then the model becomes more complex, but this still allows you then to use maximum likelihoods to model those kind of data sets.
Great. Anyone like to add anything to that?
Just one quick example using the Gaussian noise we have, right? In the tutorial, we say each data point's noise is a 1D Gaussian. So this data Gaussian noise doesn't depend on this one. So you can write the log likelihood as the summation of over independent data points. And one thing people can extend this model is you assume this data point's noise is Gaussian, but it's correlated with this data point's noise. Then usually people use a two-dimensional Gaussian. If you plot the distribution of the 2D Gaussian, it will be like an ellipse in a 2D space. It's not just a bump in a 1D. It's going to be an ellipse in a 2D. And then you should write down your probability density function with a 2D Gaussian for these 2 points. So yeah, I mean, the philosophy of building MLE for this data would be similar. The only difference is the density function would be more complicated than a than 1D Gaussian with independence assumption. So maybe it's hard to describe that, but I just want to say people shouldn't be so scared by very dependent data, because it's actually very common in real case scenario, and that's what people usually deal with in many cases. So it's not that terrifying, actually.
Great, thank you so much. Okay, we're coming up to the hour, so I think I want to give all of you the opportunity to say a few wise words to our students and TAs. Anqi, since you're on screen, do you want to give any recommendations or anything you want to share?
Oh yeah, sure.
Or just life in general, you know.
So really thanks for you all listening to this discussion, but the most important is attending the tutorial and listen to my videos and do this exercise. One thing I just want to emphasize again at the as you said at the beginning, is people shouldn't be so frustrated if they couldn't finish all the tutorials and videos, because I know they're pretty dense and there are a lot of content. So if you feel like you're missing a lot of things, that's fine. Just don't be frustrated, and feel free to ask questions to both Pierre and me. I don't know whether they have the access to email. I don't know if the TA couldn't answer the question because the videos or the tutorial are very perplexing, then we're also happy to answer the question. I will be in the discussion panel tomorrow too, and yeah, I'll be happy to answer all questions, even related to model fitting, if you couldn't figure out that. But yeah, I mean, this is a really exciting tutorial or summer school I've ever given. I actually started from scratch. I don't have any materials. I basically built up the tutorial step by step myself, but I really enjoy building up this course, and I feel like myself also learn a lot during this this process. So happy to share the video and also the experience with you all, and I'd like to hear the feedback as well, which helped me to build a better tutorial or lectures in the future. For the I don't have any technical suggestion about like what kind of model you should use.
This was great. This was great. There was no technical requirements.
Oh, okay. Just trying to encouraging people like.
Yeah, no, this is great, and you actually prompted me in a way here. So again, we apologize that we cannot possibly answer all the questions that you asked, and I see that there's another 33 questions that you asked. Please do copy them over into the NeuroStars and start a discussion there. And if you never get an answer, then please feel free to let your TA and lead TAs know, and they might be able to transmit that to us, and we can try to answer the questions that way as well. Okay, Jan, do you want to tell the students a few last words?
Yeah, I mean, thanks first of all for participating in this course. I hope you had a great day today. I know it can be overwhelming at the beginning. I think the most important thing, and this is also what I'm trying to tell my students, is that you shouldn't get overwhelmed by all the details you see. What's important is that you've seen them and that you know where you can go back to if you want to basically refine things about these details. What's more important is, I think, to understand the general concepts and how they fit together. Because this is, I think, the main aim that you should take away. You can always fill in the details afterwards, depending on what problems you're looking at. So I think that's probably what I would think is the most important approach. Another thing I think that I would recommend, and that I've learned actually fairly late, because I didn't learn this when I was doing computer science. I only learned this once I moved to neuroscience and I interacted with a lot of physicists, is always play around with everything you have. Basically ask, what happens if I move in that direction? What happens if I move in that direction? What happens if I increase the mean? What happens if I decrease the mean? You know, those kind of what-if questions, rather than just look at the equation and see, hey, this is an exponential of something, something. Right? That's not the point. The point is basically to play around with these things and ask, what happens if? Because this is actually what models are for. This is the real strength for building these kind of models. Other than that, I will try to hang out on Eurostar a little bit and answer questions if I can. And I just wish you all the best with the projects.
Awesome. Thank you, Jan. And I think I totally agree with you. Building intuitions by playing around with the models is super, super important. Patrick.
Yeah, well, continue the discussion on Eurostars, of course. I think it's I think we don't realize it really didn't dawn on me that like learning programming and learning modeling was such a social activity until like much later in life, right? Because when I was doing my PhD, I was, you know, in my closet essentially, and just you know, like reading Bishop and reading those books on my own. But I realized later there's this whole community of people that are really interested in these problems, and the amazing thing is that you have, you know, 1,700 other students that are exactly in the same situation as you, and some of them have, you know, experiences like they're more on the computer science side, and other people are more on the biology side. And so if you post your questions to Eurostars and in these other venues, which are like very public, it'll allow you to like see that there's all these people that have the experience to actually answer these questions, and yeah, lean into each other, and it's gonna be great.
We're a big happy family.
Yeah, of course we are.
No, in a certain way, that's what we're trying to accomplish here, is to make, in particular, to make the students feel welcome in this family, and also make the TAs, of course, who are doing amazing work and guiding the students to this learning experience, feel like, you know, how much we appreciate them, and really feel our love for them. Like, this is really like, us as organizers, it's hats off. So with that, thank you so much for to all three of you for joining us here for the question and answer. I think we had a really nice discussion. I enjoyed that a lot. And I'm looking forward to hanging out with you some more in Eurostars and elsewhere. See you later.
Thank you.
See ya.
Bye.
Thank you.